Yo, welcome back, DevGod here, back with another video, and today we're going to be solving LeetCode 3074, Apple Redistribution and Boxes. So this is a pretty fun little greedy sorting problem where we're going to have to figure out the minimum amount of boxes we need in order to store all of the apples given in our apple array. And we actually did come up with this really cool one-liner that I'm going to break down and explain to you that I wrote in JavaScript for this LeetCode daily problem. So we're going to go to the whiteboard real quick, because the main idea behind this problem is we're given this array apples. Now the biggest thing is they have a note right here that says, note that apples from the same pack can be redistributed into different boxes. What that basically means is we don't have to put all three apples, for example. Let me see if I can get the pencil. So like this pack of apples would have three apples included, but all three of those could go inside of different boxes. So what that basically means in a nutshell is we can take our apple array, which in this case, one of the test cases was 1, 2, 3, and just find the sum of it. So that sum is going to be that 6 right there. So our 6 total apples that we need to somehow distribute between our given boxes array. And in our boxes slash capacity array, that's going to be like the total storage capacity of each like ith box or each box that we have available. So for example, what I go ahead and do is I just sort it, and that'll make sense a little bit later. So we have like one box where we can store 5 apples, one box where you can store 4 apples, one box where you can store 3 apples, etc. And the main idea behind this problem, right, is that you could have something like 10 apples, and you want to think about it greedily. So you could have 2 boxes, for example, that have a capacity of 5. So you can store your 10 apples inside of there to use 2 boxes. So this right here, oh my god, I can like not draw today. So this right here would be 2 boxes, right? 2 total boxes that you would need to use your box number 1, box number 2. Or if you're not being as optimal, you could do something like weirder, like 3, 3, 3, 1, which would also equal, let's see, which would also equal 10 because 1 plus 3 plus 3 plus whatever is 10. But then the difference between this one and this one is that using 3 boxes in like one box, that would still equal 10. But this one, you would actually end up using 4 boxes, which would be more than the 2 boxes that you're using up here. So it's all a greedy trick of figuring out how to minimize your boxes. And I think you guys can already see that you want to go for the highest, largest capacity box in order to store the most apples for each box. So for example, if we only had 2 5s, that would be the best we can do. But if we had a box that could support up to 10 apples, then we can say like, okay, cool. This just needs 1 box. And then our 1 box is now the minimum because we'd rather have 1 box that can store 10 apples versus 2 boxes where each one of them can only store 5 apples. So that's like the whole big trick is we want to go largest capacity box first to store the most apples at a given time. So, for example, we're given 5, 4, 3, 2, 1. We want to start with the fifth box with the 5 capacity because that's going to store the most apples. One way to look at this also that I saw like my past solution use is that you start with 6 apples, you subtract 5, you would have only one leftover apple, right? But since you have one leftover apple, you need to still keep going. So then you take your 1 apple, you minus it by the capacity of 4, which basically means you store the 1 apple you have left over into the box with 4 capacity right there. And then we say that, since we hit like lower than 0 leftover apples, that just requires 2 boxes, right? So 2 boxes for this test case example would be the minimal. Another thing we can do to go about this is some people for this thing right here, including myself in the past, were using a while loop to just decrement the apple counter. So you go from like 6 to 1 by using the 5 box, and you go from like 1 to 0 by using the 4 box. My newer solution, which is more of the one-liner in JavaScript, that is actually going to use the sorted capacity box array. and it's going to apply what we call a prefix sum. It's going to apply a prefix sum to that box array. And what this prefix sum basically means, if we were just to take, let's see, how do I select this? If we were to take this box right here for number 5 and only that box, then we would say like, okay, we can only have up to 5 apples. Oh yeah, and I actually have that written right here. So the first box can hold up to 5 apples. But here's the biggest thing with the prefix sum, which is basically just kind of like adding past results to the current element in your array. So it keeps going up and up. It's like a sum of all the past results up until that point. If we were to include the first and the second box, then we could say like, okay, we have a total storage capacity of 9 total apples, which 9 total apples just so happens to be greater than my starting amount of apples, which is 6, because 9 would be greater than 6. I really cannot draw with a mouse. So basically, we can end this problem by saying, yo, like, must use the first 2 largest boxes to hold a total of 6 apples, right? And you can have like a larger size capacity, so you can go all the way up to 9 apples. But just the fact is that you want to check the first earliest point at which your total capacity you can achieve is greater or equal to your total amount of given apples. So this is kind of like the excalidraw reasoning behind why it works. Otherwise, what we do, so this first line, what we go ahead and do is this capacity sort. This is going to be great to least sorting. And basically, that's how we get our 5, 4, 3, 2, 1. That's how we get our sorted box array. Next, we're going to do the map. So maps in JavaScript basically convert elements to different elements, if that makes sense. We can also specify some different variables. This is going to look like a little bit not clean because I was doing like a little bit of a one-liner challenge. But basically, we can have a prefix sum variable, and then we can just have a constant a sum variable. Now this reduce, what that reduce does is it's pretty similar to like a sum in Python and other languages. So it's just going to be the sum of apple array slash your total apples. So that's going to be the amount of apples that you want to get sorted into all of these boxes, or the fewest boxes possible. And then last but not least, we do another reduce. So this is going to be the amount of boxes that you need. So for example, this map right here is going to be like a true false array that I'm actually casting with this plus sign. So this, I believe, would return something pretty similar to 11000. And this basically means we need the 5th in the 4th box. Let me just go ahead and copy and paste that right there as well. So we're just going to copy and paste this, doing it live. So these 2 boxes are needed, but then once we hit this box, right, the box number 3, that is when it's actually extra. Or actually, wait, reduce. Oh, actually, no, that would be more like this. Yeah, that would be more like that because the answer is expected to be 2. So basically, this represents the first point at which the p sum, or like our prefix sum, is going to be less than our apple sum. So for example, we start with 5 is less than 6, but then suddenly we have 5 is less than 9. Wait, did I do this right? Oh no, because our prefix sum would be right there. So then 9 would be greater than 6. So that's why it's actually equal to 0. And this one is actually equal to 1. Well, I mean, it's still checking. So it's still checking if 9 is less than 6, which it's false. So it's false. But then we cast it to an int, so it's actually 0. And then what we go ahead and say is like, okay, this like 9 is less than 6 is the first false that we see. We could also do a binary search. That probably would have been easier, but this is just like my own daily experience from the other day. So since the 9 is less than 6 is the first spot where we have a 0, we can then return the reduce of like all the ones we achieve. So the ones basically represent boxes where you're still underneath your total apples, so you need another box. And then you just plus one more, so that plus one takes care of your leftover amount of apples. So even though 9 is greater than 4, or 9 is greater than 6, we still have this case right here where we subtract the 5 from the 6, which that would be one leftover apple. And then that one apple still needs a box to go to, so you still need to achieve 2 boxes. And that's pretty much the same for all of these test cases as well. So you're just taking the reduce of how many ones that you found from this given map, aka the amount of boxes where your prefix capacity sum from greatest to least is going to be smaller than your total amount of apples given. And then you're just plussing 1 to take care of any leftover apples that you would need to assign to a box. And then we can just go ahead and run this. Hopefully the comments don't. Okay, good. So it looks like that still runs. Hey, LeetCode 2025 rewind. That's pretty cool. And yeah, there we go. Bada bing, bada boom. We have 0 milliseconds, pretty good. We have 56 megabytes for the memory, which is pretty okay for JavaScript. I'm not too worried about that. And we have n log of n because we're doing sorting, and we're also doing like a single pass with the map for like an O1 time complexity, and also the reduces for ON time complexity. Biggest thing is, of course, we could probably use a binary search, because the end result of checking if our prefix sum capacity is less than our total amount of apples is you're going to get, and I mean like after the map that I run here, you're going to get like an array result that's going to be similar to this, where you're still finding the first one, and then you're plussing 1, so then it's going to be these total boxes that you need. So I mean, that's just like a perfect pattern for binary search, where you're searching for like ones instead of zeros. So yeah, if you want to, you could definitely implement a binary search. Otherwise, yeah, the apple length is just 50 apples, 50 for the capacity, 50 for even the size. So it is definitely, a little bit overkill to do binary search. It's kind of optional, especially for like an easy level problem with these kind of constraints. And then we also have the input is guaranteed such that it's possible to redistribute packs of apples into boxes. So I think like either way, the solution should still work, but the problem's even nicer because it is guaranteed that there is a valid solution for this problem, which is pretty cool. And yeah, so thank you guys for watching, and of course make sure to like and subscribe for more LeetCode videos. See you guys next time. Peace.